So we're just going to start with a very brief introduction to kind of get you excited about measuring stuff and why that might be a good idea. And then, from the title of the talk, you may have figured out what this is about. So I'm going to focus on how you might weigh really, really, really small stuff. I'll give you a brief introduction to light scattering, which is really just a different word for looking at stuff, and how we use it to weigh individual molecules, as Aaron has alluded to. And then, how and why this might be useful and interesting far beyond physics. So, measurement, I'm going to use the blackboard a little bit if that's okay. Right, so, if you think about how it affects your life, the first one that you might care about, right, is time. Quite important. We're supposed to be out of here by 6:30 or 5:30, 6:30, all right, very important. The second one that's quite important, probably measuring distances. Right, and angles. That's how we build these buildings, right? And the third one is weighing things, right? So it could be a joyous morning when you step on the scale in the bathroom, or an awful one, right? But weighing stuff actually is incredibly important. You could make the argument that this is one of the most influential human inventions in terms of how it has affected society today. So here is Mesopotamia, 5,000 years ago. I found out yesterday, we had a long conversation about wine. Apparently they were big on wine very early on. And Mesopotamia was somewhere here. So this is somewhere near Iraq, and very fertile kind of part of the planet. Of course, what people did is they produced a lot of goods. Right, so food, etc. And the natural next step would be, okay, how can I trade? Right? I have A, you have B. How do we make this work? And it's the simple answer is you need a standard, right? Because I have apples and I want I don't know, bananas. Maybe it wasn't bananas. How do we make a fair trade? Right? And they actually used grains, and grains are the basis of the measure of the pound, even today. Now, you'd probably agree with me that counting, if you went to the supermarket and bought your apples, and every time somebody had to count in grains how many, how to charge you, that would be very difficult. So you work on a standard, and here's the grand K. So this is the standard kilogram. This is somewhere in a safe outside Paris. And this is really quite a dramatic development also for physicists, because it kind of formed the basis of standard units. Right? So weight, or measuring mass, really quite fundamental. Even more fundamental for chemists. Now, in terms of the kilogram, I should mention one thing. This is a map of the Earth, right? And in red, you have the countries that decided to ignore the kilogram. Right? So it's you guys, Liberia, and Myanmar. So you're an excellent company. To kind of give you, emphasize how important mass is, right? This is a periodic table. This is kind of the constituents of the universe. And it's sorted by mass, right? So whether it's civilization, whether it's chemistry, whether it's the very basics of science, mass is everywhere. Right. So how do you weigh really, really small things? So here's a human, right? About 10 to the 5 grams. Here's your barley. One of them is about 0.1 grams. Here's a single cell, 10 to the minus 9, so that's 0.0008 zeros and 1. Here you have a single virus, 10 to the minus 17, and here you have a water molecule, it's about 10 to the minus 23 grams. This is a bunch of numbers. They mean very little, but to give you an idea of the kind of challenge you're facing here, so this is 28 orders of magnitude. What's 28 orders of magnitude? So this, here you are, if you use the same axis in terms of time, this is the existence of the universe, so that's 14 billion years. This is 1 picosecond. 0.0012 zeros, right? Very short amount of time. So, you can get an idea of the relationship between these two, and that's the same kind of challenge that you would have. if you want to weigh single molecules. How do you go about that? I thought I'd use a picture of myself skiing. Right? Right. So when you do this, right, you have a certain g-force. You're trying to go around the corner, and the heavier you are, more difficult and more energy you have to use to keep the corner. Or, in other words, if you use the same amount of energy, you're going to drift further and further out, and hopefully not too far, because that's going to get dangerous. And in essence, we do exactly the same thing to weigh molecules, right? So we use something called mass spectrometers, and kind of work in the same way. You have your sample. Rather than going down a mountain, you turn your sample into the gas phase and you charge it. You turn it into ions. Okay. Then you have a tube. Okay, and maybe some magnets, and you accelerate these ions, and they go around the corner. Right. And how far they get bent around the corner will depend on their mass to charge ratio. Right? So if it's the same charge, then the heavy ones will be here and the light ones will be here. This is the world's simplest drawing of a mass spectrometer, but fundamentally this is how it works. I'm a chemist, physicist, and I will admit I didn't really worry about or think about mass spectrometry until about 7 years ago. But actually, it's kind of everywhere. Right? So we're here in Aspen. We care about sports. For example, mass spectrometers are used a lot in drug testing because they're very good at finding the metabolites that you produce when you take stuff you shouldn't be taking. Right? When they wipe your feet and your shoes and your fingers at the airport and they stick it into a machine, that's a mass spectrometer. Why? Because they're looking for traces of explosives. And in the same way, it's used in the context of environmental testing, forensic analysis. It's also used a lot in the context of life sciences. For cancer screening, drug development, unthinkable without mass spectrometry. Every drug that is out there, you have mass spectrometry involved. And also for kind of more advanced analysis of biomolecules. Now, one challenge you have here is this process is happening in vacuum, right? Because you made gas molecules and they kind of fly around. But life really likes water, right? This is how the percentage of water in our body, and in fact, water is one of the most important molecules in the context of the creation of life, which is why when we go beyond the Earth, we always look for water. That would be the first thing that enables life. So if you can't use this kind of approach to weigh molecules in water, what else might you use? Well, you could look at stuff, right? And Aaron, despite not having seen my slides, already preempted with his eggs. I have bananas, right? So if you know how much one banana weighs, then you can guess how much 5 weigh. Right? Really quite straightforward. But that could be a dangerous game, right? Because you might look at this and think it's a football, or soccer ball, as I should say. Is that the more accurate way? But clearly this is a bowling ball, so just by looking at it, it's not necessarily the most straightforward thing. What does it mean to look at something? Right? So why do you see me? The reason you see me is because there are lights up here. Light comes down from the bulb, hits my forehead, and my forehead is a little shiny. Light bounces off towards your eye, right? And the same is true with wood here and with the screen. Okay. Now, let me see. How does that work in the context of molecules, right? So light is an electromagnetic wave, so it's something like this. Okay. And visible light, 500 nanometers, the peak of the solar spectrum. This is about 500 nanometers. Okay. Now the size of a protein is on this scale. It's about this. Okay, it's maybe 5 nanometers or 10 nanometers in diameter. It's very, 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 very small. And you can do a calculation and ask the question, if I shine light on a single protein, how much light will get scattered? How much light will bounce off of the protein and make it towards your eye? And the answer is about 1 in 10 to the 9. 1 in a billion. Oh, this is billion. Is this right? It's billion. Europeans and American billions are different. 1 in 10 to the 9. So it's extremely inefficient. Right? And because it is so inefficient, kind of was generally accepted that this kind of approach is just never going to work. See a single molecule. But there is something else, another way of looking at this, which is what happens with light when it interacts with matter. Well, light has a certain speed, the speed of light, okay? And the speed of light is usually given in vacuum. But when light goes through a different medium, such as water, for example, it slows down. This is why when you have a straw inside a water glass, it looks like the straw is bent, because when the light hits the water, it gets slowed down and it bends. Right? So, in fact, the speed of light is the speed of light in vacuum divided by the refractive index, which is essentially a measure of the optical properties of matter. So if you have a single protein, and let's say, even if it's a very inefficient process, but a little bit of your light will interact with that protein, then that will get slowed down compared to the light that did not interact with the protein. Right? So you have one wave, which is your original one, the solid line, and you have another wave, which is your dust one, which is the one that interacted with it. And what happens when you take these two waves together, add them up, you get what's called interference. And that's like if you throw two rocks into a pond and you see the waves come together, you get interference between the two. And in essence, you get another wave, very small amplitude, of course, because the interaction is very weak, but it's not zero. Okay? The good news is that interference is amazingly sensitive. This is a picture of an interferometer. There are two of them in the United States, about 1,800 miles apart, and they were built to detect gravitational waves. Right? And the idea is that when you have gravitational waves come through there, the length of one arm changes relative to the length of the other arm. The change is about 10 to the minus 22. Again, a very, very, very small number, which is what took a long time to build an interferometer that is sensitive enough to see this tiny change. This has really worked. In other words, interference is really good at seeing very, very small changes. This is much, much smaller than what we need to do. It's also a much bigger operation than anything we've ever done. You know that interference is good at detecting small things because you've probably seen this, right? So this is an oil film on top of water. What happens is white light from the sun comes, it's the interface, some of it gets reflected and hits your eye. You see different colors because you have different thicknesses of oil films. Okay? So the way this works is you have your water, right? You have your oil film, and you have light, and some light gets reflected at this interface, some light is reflected at that interface. And what's the difference between these two? It's how far the light has traveled. Which is the same thing as saying, here's one wave, and here's another wave. And again, what do I get is I get interference. Why do you see different colors? Because different colors have different wavelengths. Different wavelengths will have constructive or destructive interference depending on the thickness of the film. So it turns out, difference in the color here, you can see with your eye, is due to a change in thickness of 5 nanometers. What's 5 nanometers? The size of a protein. All right? So we've used incredibly complex instrumentation, the sun, and our eyes. So without any technology whatsoever, you can see, detect, and even quantify changes that are on the order the size of a single protein. Now, where did I cut a corner here? Of course, it's only 5 nanometers in this dimension. Okay, but you've kind of summed up the signal over centimeters, because that's what you can resolve. But this is what people use in the context of microscopy. So here you have the sun, and you have your eye, right? But you can produce exactly the same thing with a lens, okay? And you shine light onto your sample, and you look at the light that comes back. So you have a light source, and you have a detector here, okay? So the light goes in, and the light comes back. And you get two waves, one from your whatever the light has interacted with, and one has been reflected at the interface. Okay, so it's exactly the same principle as here. You could call the interface the water-oil interface, and you could call your sample the oil film. Right? And this has been around for a long time, since the 40s, 80 years. Essentially, people have improved this kind of technology further and further to make more and more and more and more sensitive measurements. So why has it taken this long to get to single proteins? So here are three problems that you have. So you already know that we have very bad efficiency. Only one in 10 to the 9 photons actually interacts with a molecule, so that's very bad. Second problem is that you have too much light, and the light looks awful. So if you build a microscope like this and you look at the camera, which might as well be the camera in your phone, really all you get is an image of a laser beam. And the third problem is, even if you get rid of this background and you just look at the interface between glass and water, your background that you see, kind of rough, signal is still 1,000 times bigger than you get from a single molecule. Right? If we had done all of these calculations 10 years ago, and the only conclusion that we could have come to was that this is a terrible idea because this is never ever going to work. Right? Good news is we didn't. Right? So we kept trying. And we made a few fairly simple changes. So one of the changes we made is we just used a very simple, it's like a piece of glass with a little bit of silver on it. And essentially what it allows you to do, it allows you to change relative amount of light that is reflected and the light that comes off of your molecule. So if you reduce the amount of that is reflected, you keep the amount of light that comes from your molecule the same, what that means is your contrast goes up. You can see things better. So we went from images that looked like this to images that looked like this. Right? A huge improvement. Your signal goes up by a factor of 10, and you reduce the amount of light that hits your camera. So you kind of win twice. Second problem was the background. So here's your giant background. That's 1,000 times bigger than the signal from a single protein. And you can do a calculation that if this background moves, then it's going to produce a signal, and you can't see your protein anymore because the signal is much bigger. And the calculation will tell you that if this thing, which is a cover slip the size of your thumb, if you like, if it moves by more than a hydrogen atom, your measurement is ruined. All right? So it has to be, whatever you do has to be very, 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 very stable. Otherwise, it's never going to work. So here's the UK version of very stable, right? Vibration isolation. So you don't want any vibrations to come through the floor. The way we solved this was with inner tubes from wheelbarrows. Right? You essentially get air suspension. This is environmental insulation. So it's just a giant metal box. And on top of that metal box, you have some acoustic insulation, which is a styrofoam box for ice. Okay. And you do all of these things, and here you can do a measurement. So what you see here is just a droplet that has your proteins in it. You add that droplet to another one that is already there. You close your laser safety lid. Turn your laser on, and you see molecules. Right? And every one of these black dots is one protein. And in fact, the measurements that Aaron does at Madison every day look exactly like this. They don't involve styrofoam boxes. The instrument has gotten a little bit neater, but every single one of these black dots is a single protein. Now, I'm into building microscopes, and I had this thing, and I thought, what am I going to do with this, right? Like, what are we actually going to do with this technology? And the good news is I like beer, And so does Justin, who sits all the way in the far back corner over there. And this is a pub close to where we live, the Chester Arms. We sat in this pub in the summer of 2017, and I showed him the state, and I said, Justin, what are we going to do with this? You know, this amazing microscope, what are we going to do with it? And Justin, so happens, is a mass spectrometrist. So what would Justin say? I think we should measure mass. Right? And that's exactly what we did. Right? So here are these little black dots. Each of them is a protein. Right? And if you look on your camera, you see a signal, and then one of these proteins lands, you see the signal change. You probably agree with me that we can quantify this change really quite accurately. So the size of the step is along this axis, and then you have time. You saw the molecules bind as a function of time. You have time here. If you take a fairly standard protein and you put it onto this machine, you get this kind of scatter plot. So each white dot is one protein that binds to the surface. And where it is along here is how big the signal is, and where it is along here is time that has passed. And you can see immediately that there are bands, right? So there's definitely a band here, there's definitely a band here. They agree with me, there's one here, and if you integrate them up, you see another one and another one. And if you look at the size of the signal, you see this is exactly twice that number, this is 3 times that number, this is 4 times that number, this is 5 times that number. So what are these things? Well, the first one is 1 protein, the second one is 2, the third one is 3, the fourth one is 4, and the fifth one is 5. You can plot that on a line. So this is the mass of the protein, and this is the signal that you get. And you see we get a perfect straight line, nearly perfectly straight line. That means if you've done this for one protein, you can take any sample, read off the signal, and then you get the mass back. So what you've done is you've weighed, and you are weighing genuinely individual proteins. Okay? And as Aaron said, this was published. This is the first time I showed it was in January 2017 at this conference. It was published about a long time later because these things take time. There was another thing that happened, and that is we thought of, together with Justin, we thought of people like Aaron, and he thought, oh man, this could be really useful for life scientists. Life scientists are going to go and build this box. This is not going to happen. It took us 12 years to develop it, and I had exactly one person who knew how to build it. So that's not a realistic outcome. And we went to the lab and we looked at this thing and we thought, yeah, it kind of looks like a box, right? This almost looks like a machine. So maybe we could make a machine. And we wrote a small grant together and proposed to build a prototype of an instrument that does this, that would enable Aaron and his colleagues to do exactly these measurements. So here's the first prototype. This is February 2018. This is still 2 months before the paper was published. And as part of this, part of the kind of conditions as to why people gave us the money, they said, oh, you have to go to a conference and see if people are interested. Here we are, February 2018. Okay, this is our booth. The booth was mostly purchased at Target, which was 300 meters from the Moscone Center. So this is bed linens. This was the cheapest television we could find. This is the rickety table. We did manage to print 2 of these posters. This television, I think, is in Steve Block's house.
It is.
Because at the end of this exercise, we couldn't take the television back. And we were extremely professional about this whole exercise. For instance, we found out because we got on a plane, and about 2 days before we were supposed to leave, we figured out what the weight limit is for luggage. And it turned out this instrument was about 1 kilo too heavy. So Dan, my graduate student who designed this thing, he actually had to take the microscope apart. We had to put it into separate suitcases, fly it over to the US. Then in his hotel room, he reassembled this microscope. He was terrified that the cleaners would come in and see this thing and be worried it might be something very different. But he managed to get it to work, and here he is on a rickety table doing live demos of this technology. In fact, we sold the first instrument. There was no company. We pretended to be a company. But one of the people who came by and saw it and said, I'll be your first customer. So with that, we could start a company. And, you know, you always hear these stories, oh, in, you know, their parents' garage and all of this stuff. And I thought this was all nonsense until we did exactly the same thing. So this is Byron Burger in Oxford. This is central Oxford. This is a very well vibration isolation building from the 19th century. And the top floor belonged to was used by a software company of a friend of mine. And he said, oh, I have this available here. You see these 4 windows? So we got the 4 windows. This was our office, and this is where Dan was building the first instruments. And here is the first instrument being shipped. It's at the bottom of the stairs. We need to get 3 people to get these crates down. But in October 2018, only 6 months after the paper was published, the first instrument was actually with customers. 2025 now, 6.5 years later, right? So we've sold hundreds of instruments, and more than 50% of them are now going to industry. Right? So this is not just kind of, you know, they're really using it to develop drugs, to evaluate drugs. More than 10,000 users. Most of them are not people who built microscopes. And so that was the original vision. Many more than 100 employees across the world, Oxford and Boston. Lots of people are using it and publishing papers using this technology. So how are people using it? So gene delivery vehicles. People make artificial viruses, fill them with genetic material to get your body to produce certain things. It's like a different version of the mRNA vaccines. Right? And what they want to know is, okay, I've made a virus. Is the stuff I want to be in there, is it actually in there or not? And if you just look at it, they look the same. If you can weigh them, you know that they're different. The full ones weigh more than the empty ones. Next generation therapeutics. So there's lots of antibody-based drugs, but people are trying to develop more advanced systems for, you know, undruggable diseases. And there's a lot more added complexity. And this is something where it's being used. It's really used across life science research. You know, pretty much anyone who works with proteins benefits from having access to this technology. And in fact, there's another startup that's using the same technology to optimize batteries. Because you can use this technology to visualize the charging and kind of uncharging of batteries. Because you get different charge densities, you can visualize it using exactly the same process. All right, I want to give you one bit of science, which is an example of how this technology actually works and how this technology is useful to figure out, you know, what is going on in our bodies, if you like. Probably haven't managed to escape this thing, right? The SARS-CoV-2 virus, right? It's a nanoparticle, and it's covered by this protein called spike protein. In fact, it looks very similar. If you, for example, looked at HIV, it's also covered with an envelope protein, and it looks very similar to this one. This spike protein consists of 3 identical units. It's a trimer. And it binds to a receptor, cellular receptor called ACE2, which, among other tissues, is in your lungs. And this is why it works there. And then, of course, this is what the virus wants to do. And your immune system produces antibodies to try and stop this process from happening. Right? So if you make the antibodies, then the virus can no longer bind to the cell. And if the virus can no longer bind to the cell, you don't get sick. You again, right? This is what your immune system does. And what the vaccines do is they allow you to produce this antibody even though you don't have the virus, right? So you don't get sick. I mean, that's a general vaccine idea. But we really asked the question, and this is work done by a very talented postdoc in my group. We just wanted to understand how this interaction works and how maybe we can use this understanding in the context of drug development. Right, so I told you that ACE2 is a dimer, okay? 2 identical copies. And maybe obviously one of the very, very early attempts to develop a therapeutic against COVID was to use ACE2 itself, right? Because you know it binds to it. If you just flood the body with ACE2, then the virus will get covered in ACE2 and it can't bind to your cells. Job done. So you can titrate ACE2, you can add ACE2, and you can find out at what concentration, at what amount of ACE2 do you stop infection. It's called an IC50. So this is when 50% of the viruses are no longer infected. And it turns out that when you do this with a monomer with just one ACE2, happens over here, and if you do it with dimeric ACE2, it happens over here. That's a difference of a factor of 100 in concentration. In other words, if you're using dimers, ACE2 is 100 times more efficient than if you're using a monomer. Okay? If you remember, antibodies are effectively dimers as well, right? In the context of monomers and dimers, you can also look at patient-derived antibodies. So in Oxford, we had a very good system where scientists were able to look at the antibodies that we all produced and look at how they differ from each other, right? This is your spike protein, and they looked at many antibodies. I'm just choosing 3 here, right? And they could find out exactly where they bind, right? Which part of the spike protein do they attack? Some of them attack the blue region. The blue region is the region that is used to bind to the ACE2, so that is used to bind to the cell. And one of them bound what appeared to be off target somewhere else. And then what they did is they looked at what the neutralization efficiency is as a function of concentration for different constructs, right? So the empty circles are what's called the Fab region, essentially just one arm of the virus. So that's your monomer, if you like, of the antibody. So that's your monomer, if you like. And IgG is the whole antibody. In some cases, like 384, which was one patient, you can see that all your empty circles are over here and all your full circles are over here. And just like in the ACE2 example that I had earlier, when you have the dimer, it works 100 times as well as the monomer. Okay? Then you had other example, 150, that also binds in this region. And there's almost no difference between the monomer and the dimer. They kind of work the same way. And then you had 159, which is the one that binds off target, where you had really weird behavior, where if you just took the one arm and you looked at neutralization, it didn't neutralize at all. But when you took the full antibody, it did neutralize. Right? So you're in a situation where someone has produced an antibody that binds to the spike protein of the virus. It doesn't bind to the region that the ACE2 binding happens, but it still manages to stop the virus from infecting the cell. How does that work? Well, to visualize this, we do a slightly different experiment. So before we were just having, essentially proteins binding to a glass surface. Now we make like a membrane, and on the membrane, these molecules can diffuse. Right? So what you see in this movie here is individual spike proteins diffusing the surface. Okay. So now we can not only measure the mass, we can also measure the mobility. How fast are they moving? Okay. And our plot becomes, you have on one axis you have the mass, so this is the mass of a single spike. On the other axis, you have a diffusion coefficient, which is essentially how fast is this thing moving. If you just take the spike protein alone, you get mostly one peak with one mobility and one mass. Now, if you add your antibody, so this was 150. 150 was the one that did bind to the ACE2 region, okay, but really showed no difference between the monomer and the dimer. You see lots of binding, and this is about twice the mass. This is about 3 times the mass. Essentially what's happening is taking 2 of the spikes or taking 3 of the spikes. It's clustering spikes together. 159, which was the weird one, where the monomer didn't neutralize the virus at all, the dimer did. Here you can see this is really good at making the dimer. Okay, so it's pulling 2 things together. And when you go to 384, which was the kind of the powerhouse of antibodies, you see that it almost exclusively now cross-links. So really what the antibodies are doing, apart from just binding to these spike proteins on the surface, is they're kind of bringing them together. They oligomerize. They're making big chunks spike. And it turns out these 2 does exactly the same. Right? And here you have 2 different variants. So this is the original strain, wild type strain, and here's Omicron, which you may remember at some point there was a big deal about Omicron. What does Omicron do better than wild type? Oligomerize. Right? Now, all the experiments that we did did on this artificial membrane, and we did this at densities that are much, much lower than the density of these spike proteins on the surface of the virus. Because we can now quantify all the parameters associated with the interaction, we can predict what happens when you have density of spike proteins that you have on the surface of the virus. So the line on the far right is the bound, how much of my spike is bound to my antibody if I only had a monomer, or if I had only one spike. And this blue line on the far left is the occupancy that I get at the density of spike on the surface of the virus. And what's the difference between these two lines? About 2 orders of magnitude. Okay, so exactly the 2 orders of magnitude that we saw with ACE2, monomer versus dimer, and the 2 orders of magnitude we saw in the context of the antibodies. And why does this matter? Well, really what this curve tells you is you don't have to make that much antibody. If this mechanism is operational, you don't have to make that much antibody to neutralize the virus. Right? Otherwise, you'd have to make much, much, much more than you do here. So what did we learn? Well, this oligomerization happens whether by the antibody or whether by the cell. And of course, from a cell perspective or from a virus perspective, that's interesting, because once you have made these clusters of ACE2 and spike, the virus is never coming off the surface of the cell. That's what the virus wants. The other thing that's interesting is for what's called tropism. Right? If you think about it from not saying that the virus decides to become better or worse, but if you evolve a virus and all you do is you make the binding tighter and tighter and tighter and tighter, what will happen is you become indiscriminate. Any tissue that has ACE2 you will bind to. What you really want is you want to bind to specific tissue. And how do the tissues differ? They differ in how much ACE2 they have. So ideally you produce a system that binds to a very specific density of ACE2, which happens to be, in the context of Omicron, in your upper airways. Right? So the evolution is not in the context of better binding, it is in the context of better binding to specific tissue. And this is kind of the important message here, is that stronger is not always better. Now, when you think about therapeutics, the development of therapeutics, what does everyone do? You find molecules that bind molecules that you want to stop doing something, right? And traditionally, people have always thought, oh, you want tighter binding, tighter binding, tighter binding, tighter binding. But then you can have issues because the drug doesn't just bind to the tissue that you want, it binds everywhere and creates problems. So maybe here is an approach that you can use to develop slightly different drugs. Right, so I hope I've shown you that there is a good amount of life in measuring the mass of single proteins just by shining light on them. But I just want to finish with one bit. We heard the Aspen Center of Physics. You're all taxpayers. I'm the taxpayer. This is publicly funded research, right? So what do we do with all of that money? This is about as fundamental as it gets from the outset, right? 15 years ago, my job was build a more sensitive microscope. Microscopes are only used for imaging. Okay? We really just wanted to figure out what's the smallest thing we can see. When we started this in 2006, it was accepted this would never work. If I had written a proposal and said, oh, here's what we're going to do, not only are we going to see single molecules, we're going to measure their mass, and people are going to use it for optimizing gene delivery vehicles, that may have been the end of my career, right? Because that's just insane. Nobody would have believed us. If you can, do a very simple calculation today in terms of the investment, private investment into the company, in terms of how the technology is being used, in terms of the employees all over the world, more than 100-fold return on the investment by the taxpayer into what was really, really, really fundamental research. I would have loved to tell people 10 or 15 years ago, trust me, I know this sounds really basic, but there's going to be lots of applications, it's going to be great. Most of the time we don't know. The thing that matters is that you really push the boundaries of what is possible, and good stuff happens. In a weird way, this is a completely accepted approach in the context of investments. If you think about venture capital, the idea behind venture capital is support 100 companies and only 2 of them make it. Right? You don't expect every company to make it. Say, I support good teams and good people and, you know, good ideas, and some of them will go. And it is really, feel very strongly about this. It's kind of really the same thing in the context of what appears to be, why are you doing this? Why are you using my money to build better microscopes? What a waste of time. Well, sometimes you need a little bit of patience, and things happen. You go to the pub and you talk to Justin, and there's a lot of change. I want to finish with the other thing that's important. Is Brenda here, by any chance? You have great ideas, and you do good science, and you know, you find investors and they build companies. You have all of these things. They are irrelevant without the people who do the work. Okay, no matter how good the technology is, no matter how much money somebody gives you, if you don't have the right people, it will not go anywhere. So I'll finish with a picture of my group. This is last year, our Christmas dinner, very Oxford. They are the people who really do the work. You know, they are the ones who go into the lab, and they are the ones who fail for 3 years or 4 years, and then eventually they get stuff to work. You know, this took 15 years. Hats off to them, right? This kind of work is about as frustrating as you can imagine, but sometimes it works out. And of course, I need to highlight Justin, without whom there would be no mass. So with that, I think I'm at the end of my time, and I'll be happy to answer any questions you may have. Thank you. Yeah.
So is this a relative measure of mass, in the sense that, you know, heavier molecules will slow the light down more, so you get a different interference pattern?
Yeah.
And do you just calibrate by saying, well, when we do this with a molecule of known mass, that gives us our reference unit, and then everything is relative to that?
Okay, so I'll repeat that. So is this an absolute measurement? Is it a relative measurement? And do you get different answers for different molecules? 100% it's a relative measurement. In a certain way, that's even true for mass spectrometry. Mass spectrometry, you measure mass over charge. Okay, you don't measure mass directly, you measure mass over charge. That is exactly what we do. We take a sample of known mass and we do a calibration. In many ways, everything works like that. Right? It's very, very difficult. I mean, the Grand K, if you like, that is an absolute measure of 1 kilogram. But again, that is, somebody decided that piece of metal is 1 kilogram, right? Where we are lucky is that most biomolecules are kind of the same in terms of their optical properties. And you know that if you take a normal microscope and you look at a cell, it just looks like a blob. Just blah. Because it's all the same stuff, right? And proteins are all made of 23 units amino acids. They're all the same. How many is it? 20. I meant that. Well, there's some artificial ones. Can we edit that out? So they're all the same stuff, right? Different proteins have them in different order and different amounts. It's all the same basic building block, and therefore the optical properties are the same, and therefore if you use one protein to calibrate, it works for all of them.
So if you have 2 proteins of different structures, that will still affect the light based primarily on their mass, not because of the shape of the
The reason why the shape, well, the reason why the shape doesn't matters very little, to be very accurate, is, remember this relative size? Because the protein is so much smaller than the wavelength of light, the light can't really tell what it's just too small. It all looks like a dot, you know, whether it's a slightly bent dot or slightly oval, the light doesn't really know. So there is an effect, but it is very, very, very small, and it's below the measurement error that we have anyway, so we don't really worry about it. Yeah.
Can 4 wheelbarrow inner tubes really reduce vibration to less than the diameter of a hydrogen atom, or did you simplify that for us?
No, that's generally true. So, I mean, I can tell you exactly how this works. So usually, if you're an optical physicist, you build microscopes or spectrometers or anything, what we use is we use these tables, optical tables. It might be the size of a pool table, for example, but it has a big layer of stainless steel and then lots of structure in it and vibration isolation to kind of minimize environmental perturbations. The first instrument that we built, of course, we built on one of these tables. The first measurements that we did, the only way we could do the measurements were the two people. One person was standing in front of the computer holding the mouse. The other person was standing next to the thingy with the pipette. And then the person would pipette a little bit, move the hand away, the other person would click. Nobody could move or breathe for 30 seconds. Because any perturbation, the slightest perturbation, would cause this level of vibration. The wheelbarrow, I mean, it worked. What do you want me to say? It did it, right? Once we built that thing, a giant metal box, the metal, was 2-inch thick metal, and it was heavy, weighed 100 kilos or something like that. Then, people could walk around and have a chat, and that really did the job. And in essence, that's what the commercial instrument, does in a much more elegant fashion, of course, than the wheelbarrow. Yeah.
You said that 15 years ago, this kind of work would be impossible. In the next 5 to 10 years, where do you think this technology could take modern science?
I mean, it's always a little bit difficult to look into the future because most of the time, we've been operating at the very limits some time, and it's a little bit difficult to imagine, another order of magnitude improvement. But mass spectrometry has been around for 100 years, right? And originally it was just small molecules mass measurement, and today you see where that technology is being applied across all of everything, right? And these things do take time. Do I think that there's a fundamental reason why this technology could not undergo a similar kind of evolution in terms of how it's being used and how it's being applied and where it's being applied and what kind of problems it can be used for? No, right? In principle, you have one molecule, you measure the mass. We can do a back of the envelope calculation that says, with the technology as it is today, if we just did the experiment a little bit better, we would open up another order of magnitude of applications. So I think probably its biggest, there are two sides of the impact story. One is I do think that this technology will have a substantial impact in the context of drug development. The reason is, we started with small molecules, then went to antibodies, and the next step is just bigger things. Whether it's viruses, whether it's mRNA and lipids, whether it's multi-specific antibodies. There's more heterogeneity and more complexity. And mass spectrometry really struggles with the heterogeneity. Really difficult to deal with the fact that not all molecules are exactly the same. And this technology does not. So I do think that as it improves, as it is not only used, by me with a pipette, but as it is next to a bioreactor when stuff is being made in a pharmaceutical company, I think this is where the impact will be massive. But who knows, right? This is 6 years old, right? It's really early doors. Yeah.
Do you get better results with shorter wavelengths, like if you use, extreme UV or X-rays?
Yeah. The question was whether we get better results with shorter wavelengths. It's a very good question because shorter your wavelength, right, the better that relationship. It turns out shorter wavelengths scatter light better, which is why the sky is blue. So you're absolutely right. Bluer wavelengths are better. There's one problem, and that is optics, cameras, everything is optimized for the visible. So you can't go and just build a microscope that works in the ultraviolet and has the same detection efficiencies. You have the same lasers and the objectives. And is it out of the question? No. Is it much harder? Yes. There's a second problem. The shorter the wavelength, the higher the energy. Essentially, what you start doing is you start blowing stuff up. And we have some instruments that are very good. I mean, the box that I showed you, the big blocks, its nickname was Death Muncher because it was really, really good at burning everything, and that was still far away from the ultraviolet. Any other questions? Oh, I think it's time. It's exactly 6:30. This is where we were supposed to stop, so we can measure it.